Designing an intuitive user interface for controlling assisted robots remains challenging. Most existing UIs leverage traditional control interfaces such as joystick, handheld controllers, and 2D UIs. Those users have limited availability to use their hands for other tasks. By exploiting the user's existing abilities, augmented reality head-mounted display user interfaces offer the possibility of hands-free interactions through their multimodal input capabilities, thus potentially making these interactions more intuitive and easy to perform, and increasing the probability of acceptance by non-expert users. Towards extending the state-of-art in the domain of UIs for leg manipulators, in this work we provide a user study comparing an augmented reality head-mounted display user interface we developed for controlling leg manipulators against an off-the-shelf control methods for such robots. We made this comparison baseline across multiple factors relevant to a successful human-robot interaction. We focus on the UI as the main independent variable in our study. Nevertheless, the user trials also involve various task categories. For the obstacle-free navigation task, the participants navigated with the robot across an obstacle-free corridor while visiting a total of 3 waypoints, which were placed 5 meters apart in a straight line. The second task involved navigating through multiple door openings and taking the robot up a flight of stairs, while stopping at 3 waypoints as well. Based on their experiences, the participants had to choose their preferred UI to complete the final task, which involved picking an object from the floor while the robot remained still. We use a vision-based colocalization method to colocalize the robot and the head-mounted display under a global coordinate system. Such method generates an offset on the head-mounted display estimate of the robot pose, which increases as the robot moves away from the common reference frame, known as an anchor. To reduce this offset, we extended the capabilities of our UI to support multi-anchor vision-based colocalization. Our results show that the AR UI significantly increases immersion compared to traditional control methods, thus promoting engagement and enjoyment in the task without compromising other HRI metrics. However, performance and cognitive workload metrics were initially negatively affected by our UI. To improve these metrics, we exploited a cognitive offloading technique used by some of the participants with the controller. These participants rotated their bodies to align themselves with the robot to facilitate its positioning. Similarly, we added a new functionality to the AR UI that allows the users to position themselves where they want the robot to go and orient themselves in the direction they want the robot to face. Then, after receiving a voice command, the robot positions itself matching the required pose. This new feature drastically improved the performance and cognitive workload metrics.